Uh, Before we get into the pH scale, since we're talking about acids, here are the 6 strong acids that we would like you to memorize. So hydrochloric, hydrobromic, hydroiodic, they are the binary strong acids. And then here are the ternary strong acids, HNO3, HClO4, and H2SO4. Strong bases, we're going to talk about those in a moment. There are 12 of those. These are the main 6. But strong bases are any alkali or alkaline earth metal paired with hydroxide. So any group 1 or group 2 metal paired with hydroxide. Paired with hydroxide. So, lithium hydroxide, sodium hydroxide, potassium hydroxide. You keep going down group 1. Rubidium hydroxide, cesium hydroxide, francium hydroxide. And then the alkaline earth metals, right? So group 2, beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. They're all strong bases. So really there's 12 of them. Those are the main 6. You don't need to memorize the strong bases. That's the good news. Because as long as you have a periodic table, take any group 1 metal and any group 2 metal, pair it with hydroxide, you got yourself a strong base. So there's 12 of them. There's 6 alkali metals and 6 alkaline earth metals. So those are the nice things. Nice things you don't have to memorize. The strong acids you got to memorize. Really positively must memorize these 6 strong acids. It's going to be so important, especially for tomorrow in lab when we get to the acid-base properties of salts. Cool. So what makes an acid strong? Like, why are those 6 acids strong? What makes a base strong? Well, strong means fully dissociates. So completely dissociates. So a strong acid, this is why I was using that single-headed arrow before with HCl. A strong acid is just one that completely breaks apart. So if I put 100 molecules of HCl in water, all of them break down, okay, and I will get 100 hydronium ions, and I would get 100 conjugate base chloride ions. A weak acid like HF is not one of the 6 strong acids, so it's HCl, HBr, HI, HNO3, HClO4, and H2SO4. HF is not one of those. A weak acid, notice since this is weak, I'm using an equilibrium arrow because it's not going to completely dissociate. A weak acid, if I put 100 molecules of HF in water, they do not all dissociate. Maybe only 5 of them dissociate. 95 of them stay together, which means I only get 5 hydroniums and 5 F minuses. Well, HCl, since it fully dissociated, made way more H plus ions than HF, which only partially dissociated, right? So maybe, 100% of these molecules dissociated and only 5% of these dissociated. You're going to have way less H plus ions or H3O plus ions in weak acids. So strong just means fully dissociates. And since it fully dissociates, it makes a lot of H pluses, or if it's a base, OH minuses, which is what makes it strong. Right. Conjugate strength, super duper important for tomorrow in lab when we talk about acid-base properties of salts. The conjugate of strong things is weak, and the conjugate of weak things is actually a pretty good or okay. So what do I mean by that? Well, let's talk about that. So for example, we can make an inference about the strength of a conjugate based on the strength of the acid or base, the original acid or base. So for example, if I have HCl, it's my acid, this is I want the conjugate base. Conjugate base is chloride. Since this is a strong acid, the conjugate is going to have the opposite strength. So if this is a strong acid, then this is a terrible base. In fact, it's a non-existent base. The conjugate of something strong is insanely weak. Okay? Now, the opposite is also true. If I take something like, acetic acid, HC2H3O2, and I put its conjugate over here, C2H3O2 minus, this is a weak acid. How do I know it's a weak acid? It's not one of those 6 strong acids that I need you to memorize. If you're an acid and you're not one of those 6 strong acids, then you have to be weak. So this is a weak acid. What that means is that the acetate polyatomic anion is actually an okay base. It's okay. We're not going to call it strong, okay? Because the strong bases are the alkaline, alkaline earth metal hydroxides. But it's a decent base. It's okay. The conjugate of something strong, terrible. Conjugate of something weak, decent. Okay. You can use this to predict the direction of an equilibrium where the stronger thing is going to want to dissociate more than the weaker thing. So let me show you. We're going to try to predict for this first reaction which side the equilibrium is going to lie on. Now, if we look on the left, we have HCN, weak acid. If we look on the right, we have HNO3, which is one of our 6 strong acids. HNO3 is going to want to dissociate more than HCN. So this reaction is going to go this way from right to left. Okay, the HNO3 is going to want to dissociate. So the equilibrium will lie on the left-hand side. This is the stronger acid. The stronger acid is going to be the one that wants to dissociate more. Now, sometimes if there's no strong acid involved, we need a table of acid strength, something like this, or we at least need the acid dissociation constants, which we'll get to in a moment. On this side, my acid is HF, and on this side, my acid is NH4+. So if we look at the table, HF is here, and NH4+ is here. So HF is a stronger weak acid, it's kind of like an oxymoron, than the ammonium ion. So HF is going to want to dissociate more than NH4+, so this reaction's equilibrium would lie on the right side, on the product side, because HF wants to react more than NH4+. Awesome. So now, how do we measure acid strength? Well, the first time in school that you may have measured acid-base strength was with litmus paper, although this stuff is kind of going by the way of the dinosaur. Litmus paper is the most simplistic and tells you the least amount when you are measuring acids or base strength. There's 2 kinds of litmus paper. Red litmus paper, which turns blue in the presence of a base, think blue base. And then there's blue litmus paper, which turns red in the presence of an acid. So in order to identify something, you really need both types of litmus paper. A substance is neutral. If you put red and blue litmus paper in it, neither of them will change color if the substance is purely neutral. Nowadays, we have indicator paper, which changes a whole rainbow of colors, and you can match it up with a key. And, if this thing turns green, it's a pH of 8. If it turns, orange, it's a pH of 3. If it turns like, deep red, it's a pH of 1. If it turns dark blue, it's pH of 13. You can pair it up with a variety of colors. It actually has multiple indicators on it instead of just the litmus indicator, and that's how they get that rainbow of colors. The indicator paper is nice because it tells you, you know, it tells you a range. The litmus paper is dangerous because I could dip blue litmus paper in acid, like lemon juice, and it could turn red, and that's safe. And I could dip it in 12 molar hydrochloric acid, and it could turn red, and that's not safe. And you don't know which is which, But at least with the indicator paper, it's going to tell you, the relative ballpark acidity, and you can take proper safety precautions with that stuff. Alrighty. The pH scale. Man, let's talk about the pH scale. The pH scale was invented for non-chemists. I personally hate the pH scale because I don't need the pH scale. Let's talk about why chemists don't need the pH scale. And then let's talk about why we invented the pH scale for the average Joe. So we define every single scale needs a standard. We define pure water as our standard for being neutral. So pure deionized water is neutral. Now, we actually already talked about pure deionized water. We said that autoionization of water reaction we said at 25 degrees Celsius, this reaction happens such that the hydronium is equal to 1 times 10 to the negative 7. And the hydroxide is equal to 1 times 10 to the negative 7. It's actually what we define a neutral solution as. A neutral solution is defined as having a hydronium ion and a hydroxide ion concentration of 1 times 10 to the negative 7th molar. If a solution is acidic, then that means that your hydronium ion concentration is greater than 1 times 10 to the negative 7th. So the hydronium ion concentration goes up, and by default, the hydroxide would then have to go down. So if I'm sending the hydronium up, the hydroxide has to go down. Why? Because no matter what, when I multiply these two together, they have to equal 1 times 10 to the negative 14th, the equilibrium constant, also known as the ion product constant, for the autoionization of water. So they are inversely proportional. If the hydronium ion goes up, the hydroxide goes down. So an acidic solution is defined as a solution where the hydronium ion concentration is greater than 1 times 10 to the negative 7th. And the hydroxide, by contrast, would also be less than 1 times 10 to the negative 7th. So I don't need the pH scale, because if you just tell me the hydronium ion concentration, like if you tell me the hydronium ion concentration is 3.5 times 10 to the negative 4th, I know that something times 10 to the negative 4th is bigger than something times 10 to the negative 7th, so I know that's an acidic solution. I don't need a pH scale. Okay, but the average Joe does not understand scientific notation. They're going to need it. We'll talk about that in a second. A basic solution is going to be one where I have less hydronium than 1 times 10 to the negative 7th, and by default have more hydroxide. So the hydroxide is higher than the hydronium. So a basic solution is going to be one where the hydronium ion concentration is less than that neutral value of 1 times 10 to the negative 7th molar, and the hydroxide would be greater than that neutral value of 1 times 10 to the negative 7th molar. How we feeling? Do you see why chemists don't need the pH scale? Here's the problem. Okay, the average Joe does not understand scientific notation. So if I said to the average person, if I say, hey man, the hydronium ion concentration is 3.5 times 10 to the negative 13th. Well, the average idiot out there is going to say, well, negative 13 is bigger than 7. That's acidic. That's not. Negative 13th is smaller than negative 7 is basic. So chemists tried, and I don't think they'd achieved it, but they tried to simplify this for the average Joe that doesn't understand scientific notation. And they said, well, if we got rid of the scientific notation, then we could come up with this scale where they don't have to like read numbers and understand decimals and negative exponents. And they said, well, I know how to get rid of this scientific notation. We could just use logarithms, because a log is a base 10. Then you could get rid of this times 10 expression. The problem is simplifying something with logarithms is kind of an oxymoron, right? It's kind of stupid. So here's it, because it doesn't, nobody simplifies something by using logarithms, right? People don't understand logarithms either. But here's what chemists came up with. They came up with this crazy idea that unfortunately stuck. They say we could define the pH of a solution as the negative log of the hydronium ion concentration. So if you take the negative log of your H plus ion concentration, then you could calculate the pH. And what it'll do is it'll eliminate the scientific notation, and it'll eliminate the the need to compare it to this. And they said essentially this. They said that if your pH is 7, you'll be neutral. If your pH is below 7, you'll be acidic. And if your pH is above 7, you'll be basic. Well, let's test this out. Let's plug in 3.5 times 10 to the negative 13th. Now, before we plug it in, that is smaller. That's a hydronium ion concentration that is less than 1 times 10 to the negative 7. That's going to be a basic solution, right? That is less than that. But let's plug it into here and see what we get. So you're going to do negative. So on your calculator, You want to do negative, not the subtraction sign. Well, it's the I-83. Obviously, it's down there by the decimal. Negative. Then you want to hit log, not natural log. No, 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 no. Regular old log. And then I do 3.5 e negative 13. So I'm popping it in there like that. Oop, 3.5 e negative 13. That's how I put it in there. And I get 12.46. 12.46 as my pH. That would be a pH of 12.46. And indeed, that is basic is above 7. So what did taking the pH of that do? Well, it took this number that was in scientific notation and gave us a number that doesn't have scientific notation. That's all it did, which in my opinion is stupid. This is stupid, right? Force people to understand scientific notation. We don't need to invent the pH scale. I think it's stupid. Okay, but it is what it is. It's handy, I guess, when you're testing like pools or hot tubs or something to have, instead of printing scientific notation on the test strip bottle or something, but whatever, right? It's not needed. We don't need the pH scale. Yeah, it's not needed. But that is our definition, right? We can try another one, if we plug in a value that is greater than 1 times 10 to the negative 7. So let's say our hydronium ion concentration is 1.9 times 10 to the negative second. Go ahead, calculate that H plus ion concentration. Oh, we'll talk about sig figs here in a second, by the way, with logarithms. So if you punch in negative log of 1.9 e negative 2, we get a pH of 1.72. 1.72. Here's the rule for logarithms. You ready? The number of sig figs in your concentration. That's how many places past the decimal you have to go after you've taken the logarithm. So 1.9 e times 10 negative second. That's got 2 sig figs. So we got to go 2 places past the decimal. So 1.72. We went 2 places. What comes in front of the decimal doesn't matter. It's just what's after the decimal. That's how many place values past you got to go. If this was 1.90 times 10 to the negative second, that's now 3 sig figs. We'd have to go 1 place further. That'd be 1.721 as our pH. Okay, so that's what changed. Yeah, I know it's kind of a way. Now, when we got to do that rule in reverse, it gets really crazy. Okay, but that's our pH rule for that one. Okay. Oh, obviously, and I should mention it, if we plug in 1 times 10 to the negative 7th, which is our neutral pH, or neutral hydronium. If we plug that in the calculator, go ahead, negative log of 1 times 10 negative 7th, that's a pH of 7.00, and that is indeed, that's why that's neutral. So if you've ever wondered, why is a pH 7 defined as neutral? It's because neutral water, so regular old water, has a hydronium ion concentration of 1 times 10 to the negative 7th, so that's why it's a pH 7. Huh? Cool. There is a pOH scale. I know, right? Because in water, you get hydronium and hydroxide when it undergoes autoionization. We could have just as easily picked a scale that checked out the concentration of the hydroxide on. Okay, and that's called the pOH scale. And it's going to have the exact same formula. The pOH is the negative log of the hydroxide ion concentration. And it is the complete inverse of the pH scale. So on the pH scale, right, a pH of 7 is neutral. That's the only thing that the pOH scale has in common with the pH scale. That's neutral. On the pH scale, if your pH is less than 7, you are acidic. But on the pOH scale, if your pOH is less than 7, you are basic. And on the pH scale, if your pH is above 7, you are basic. And on the pOH scale, if your pOH scale is above 7, you are acidic. But wait, there's more. At the end of the day, your pH and pOH of a solution have to add up to being 14. So here's a really important equation. The pH of a solution and the pOH of a solution have to equal 14. Here's what that means. If you have a solution that has a pH of 3, then the pOH of that same solution must be 11. That solution would have a pH of 3 and a pOH of 11. They have to add up to 14. If you have a solution with a pH of 10, then the pOH must be 4. Okay, and that's how we can, very quickly get there. Okay, so that's an important equation. So you use the pOH formula just like the pH formula, where you just plug the hydroxide concentrations in here, right? We just plug the hydroxide. So, if my hydroxide ion concentration was 5.4 times 10 to the negative fourth, if we plug that in there, negative log of 5.4 e negative 4, 2 sig figs. So I'm going to go 2 places past the decimal. The pOH is 3.27. And maybe you want to get a pH now. Well, here's the handy thing. The pH plus the pOH has to equal 14. So 14 minus the pOH will give me the pH. So if I do 14 minus 3.27, we get 10.73. That's the pH. So a solution with a pOH of 3.27 has a pH of 10.73. Okay. So again, if you have a pH, you can get a pOH. If you have a pOH, you can get a pH. Just 14 minus that value gets you the other one. So that's a pretty handy formula. That's pretty sweet. Cool. Oh, one thing I do want to impress upon you, almost forgot, this one half slides, so I don't forget stuff, is that the pH scale is logarithmic. And I really want to emphasize what that means, because I think a lot of people don't grasp, this very important concept. A common misconception that people have about the pH scale is they think it stops at 0 and stops at 14. They think all bodies fall between 0 and 14. That is 1,000% wrong. You can have acids that have a negative pH, and you can have bases that have a pH above 14. Okay. For example, well, we'll get there in a second. But the strongest acid known to man has a pH of negative 26. So for now, the record is negative 26. And there are bases that are up in the 20s, but not nearly as scary as this negative 26 guy. This is fluoroanemonic acid. I'm going to impress upon you just how crazy that is here in a second. The pH scale is logarithmic. So here's what I want you to really understand about that. If I have a solution with a pH of 4 and a pH of 3, how much more acidic is the solution with a pH of 3? Well, they differ by a single pH unit. This is a log base 10 system. So each whole number on this system differs by a factor of 10. A solution with a pH of 3 is 10 times more acidic than a solution with a pH of 4. What about a solution with a pH of 2? How much more acidic is that than a pH of 4? Well, a pH of 3 is 10 times more acidic than a pH of 4, and a pH of 2 is 10 times more acidic than a pH of 3. That's 10 times 10. That solution is 100 times more acidic, right? If I have a pH of 1, that would be 1,000 times more acidic than a pH of 4. I want to put into perspective how crazy fluoroanemonic acid is. Concentrated hydrochloric acid has a pH of negative 1.08. So if you took hydrochloric acid right out of the bottle that we have in the back of the lab, the concentrated stuff, okay, cannot get any stronger. It's negative 1.08. So you can see it's below 0. Fluoroanemonic acid is negative 26. At first, it looks like fluoroanemonic acid is 25 times more acidic, but it's not. So logarithmic scale, it's 10 to the 25 times more acidic than concentrated hydrochloric acid, which would mess your day up real bad. Fluoroanemonic acid is scary. It's a classification of acids called a superacid. It was discovered by a guy by the name of George Olah, and it is some crazy stuff, absolutely crazy stuff. I worked with it. I'm one of a handful of people that got to work with it. It's terrifying. You can't open it. Like I couldn't open it in this room because it would protonate the water vapor in the room, and I would breathe that in, and my lungs would melt, and I would die. So that would suck. So you got to work with it in one of those like nitrogen glove boxes or argon glove boxes.